All right, so in this video, I'm going to teach you how to hack smart contracts on the blockchain. All right, this is such a huge topic. People have asked me about this a lot, so I'm finally making this video for you all because, there's so much money out there secured by blockchains, and many of these smart contracts are vulnerable to hacks, and we've seen lots of cases where people take millions of dollars out of smart contracts with the exact technique that I'm going to show you in this video. So this is something called Reentrancy. It's one of the most common ways that smart contracts get hacked. And so I'm going to teach you everything you need to know about it in this video. So if when you're around here, hey, I'm Gregory. On this channel, I turn you into a blockchain master. So if that's something that you're interested in, then smash that like button down below for the YouTube algorithm and subscribe to this channel. And if you want to know how to master blockchain step-by-step start to finish, then head on over to dappuniversity.com/bootcamp to get started today. All right, so let's talk about this reentrancy hack and why you need to understand it. So first of all, I'm not teaching you this so that you can actually go and steal somebody else's money. It's not why I'm making this video. This information is useful for two big reasons. If you can do this, you can disclose this vulnerability to other people in terms of bug bounties, and in many cases, you can make a lot of money for doing this. We've seen lots of stories of developers making over $1 million in a day just for disclosing smart contract security vulnerabilities. So it also pays to be honest when you find this stuff. The other reason is to protect yourself and your own smart contracts or your team's smart contracts if you're putting them out there, because you have to understand what security vulnerabilities are and think like a bad guy so you don't fall victim to this attack yourself. So that being said, let's go over the shoulder and get started. All right, so let's look at how this reentrancy attack works. So essentially, let's think about a bank smart contract as an example. So what does this bank smart contract let people do? Well, it lets people deposit funds into the smart contract and also withdraw them. And inside the smart contract, it keeps track of, the entire balance of everybody who's ever deposited. Okay, you can see this right here. This is like 100. We'll just call this Ether for now. It's a pretty good, easy example of a cryptocurrency that can be deposited here. So 100 Ether in total, let's just say spread across 10 different depositors. But here you can see this external wallet who's interacting with it. They can deposit and withdraw. This will be the user in this case, and they've only deposited 10 Ether. Okay. So essentially, in this case, an external wallet should only be able to call this withdrawal function once they've deposited to deduct their balance of 10 Ether. And there's really no way for an individual wallet, let's say somebody who's just got their MetaMask wallet connected to the blockchain, to hack this smart contract and, manipulate this or exploit this withdrawal function in any way. However, if they create a smart contract and perform a reentrancy attack, then they could attack the smart contract and drain the entire smart contract balance of 100 Ether instead of their balance, which is 10 Ether, if they use an external smart contract and if the bank smart contract has a reentrancy vulnerability. So what is it? What is reentrancy? Well, it is basically what it sounds like. You're essentially, let's just look at the withdrawal function in this case. This is the function that's potentially vulnerable to a reentrancy attack. So reentrancy means you re-enter this function while you're still calling it. So basically, you can see this here where in a normal scenario, whenever the user calls this function, they should only be able to call it once and, say withdraw their entire balance, which is 10 Ether in this case. Well, a normal user should only be able to call this once, and whenever they call the transaction on the blockchain, it just does one instruction, does withdraw. However, if you use a smart contract, you can re-enter this function in some cases and keep withdrawing the balance while the withdrawal function is still being called, and basically call this in loop so that, you keep withdrawing the entire balance in increments of 10, which is your deposit, over and over again until the entire smart contract is drained. You're re-entering this function while you're still calling it, okay? So that's what it looks like from a high level. You have this bank contract that has this withdrawal function. It has a reentrancy vulnerability, which lets an external wallet, the attacker in this case, use another smart contract to call this withdrawal function and then keep calling it while it's still being called in loop until it drains the entire balance from the bank contract. So that's just a high-level overview of what it looks like, right here. Let's go ahead and jump into the code so you can actually visualize this, see how it works, see if your smart contracts are potentially vulnerable to this and how you can fix it. Now let's go ahead and grab the coding solution for this project so you can see how reentrancy attacks will work. So head on down to the description below this video. You're going to find a GitHub repository that has a coding sample here. So go ahead and grab that link. All right. Go to your terminal and say git clone. All right. Then paste in the URL. So I've already done this. It's going to give me an error here. But whenever you do it, you should see a success message. So I'm going to enter into this newly cloned directly like this. I'll cd reentrancy. All right. And then next, we need to install the dependencies for the project. Okay, we can install your dependencies with Node like this. So npm install. All right, I've already done this step as well, but you should wait for your dependency to finish. You'll see them there. All right. And then you need to make sure you have some basic dependencies on your computer before you can run this example. Even if you don't, run it completely, okay, you can still grab the code. You can still make sense of it. But you need Solidity, which is going to be installed through Hardhat, okay, which is going to get installed with that npm install like this. So the biggest dependency you need is, let's see, Node.js for managing your packages. And once you run Node.js, you'll get Solidity, you'll get Hardhat, you'll get Ethers.js, okay? So make sure on npm install, that's going to give you Hardhat. Like I was saying before, we're going to use Hardhat for the contracts here. So you can do npx Hardhat compile just to make sure everything's working properly. Okay, I've already done this step as well, so you shouldn't see too much. You might see this license identifier. We can fix that here in a second. But that will ensure that everything's working properly. So I'm going to go ahead and open up this code in my text editor here. I'm just using Sublime Text. You can use whatever text editor you'd like. And you can see we've got all our basic Hardhat configuration inside of here. We've got this Hardhat config file. We've got our package.json file, right? It's got all our dependencies that we need. But the smart contracts where we can actually visualize this reentrancy attack is inside of here. Okay, so, in here, contracts directory. So here's the bank smart contract. That's exactly what I was talking about here, okay, where, the user should be able to just theoretically deposit funds and then withdraw. And then, in this scenario, we have an attacker smart contract, which is this exploit right here. That's going to be this, attacker.sol. So let's start off with the bank and see how it works, see how it's vulnerable to this reentrancy attack, and then how we can fix that problem, okay? So the bank is really simple. It's really, really simple. It's just a simple smart contract that's called bank. What it does is it has a mapping inside of it that keeps track of, the balances. It lets people send Ether to the smart contract, either Ethereum, cryptocurrency, or Ether, and then it keeps track of everybody inside this balance mapping. If you're not familiar with mappings, basically they just store key value pairs on the blockchain. You can kind of treat it like a database in this sense where you give it the address and then it returns a number which corresponds to the balance of the person who deposited. And they call this deposit function. So they basically just say deposit. It updates this balance of message sender. That's what msg.sender stands for. This is the amount of Ether sent in with the transaction. And then it just increments it by message value. So MSG message value is the amount of Ether assigned to the transaction as well. So message sender is the address of the person sending. Message value is the Ether amount. And so that gets stored here. All right. And then this, let's just see here. This withdraw function is how the person withdraws from the bank. All right. So it's got two functions, deposit and withdraw. So whenever they deposit, and this is where the vulnerability lies, right? This is what you really want to pay attention to. I'll even bump this up so you can see it. So the withdraw takes the deposited amount. So essentially it gets their balance from this mapping. And then it says basically their address, whoever's calling this function, send Ether. Okay. So take your balance out of the mapping and then send Ether, the deposited amount to the person calling this function. And then it resets their balance to 0. Now, here's the function that has reentrancy vulnerability, because what can happen is essentially while this function is being called, okay, by another smart contract, if message sender is a smart contract in this case and not an externally owned account like a MetaMask wallet, then that smart contract can essentially call this deposit function and the withdraw function at the same time, okay, over and over again. And when it does that, it can essentially drain the entire smart contract balance. So why is that? Because if it calls deposit, all right, then essentially it's updated the mapping, and essentially you can just withdraw the amount from that over and over again. Okay, so I'll show you what that looks like. Inside the attacker, this is the second smart contract. All right, so you can see it here. Essentially, that's what you're going to do. The attacker can call the bank's withdraw function, deposit and withdraw at the same time, and deduct this balance. It's let's say it deposited 10 ether. Well, it can just keep depositing 10, withdraw 10 over and over and over and over again until it's drained this entire balance of 100 ether. So that's what it looks like right here. So the attacker essentially understands the interface for the bank contract. That's what this is. We import the interface for the bank right here. We don't actually import in the file. We just create an interface that understands the functions like the deposit withdrawal. That's what a smart contract interface is. It's just kind of like a skeleton for the smart contract that tells you what the functions look like and what their arguments are. Okay. So we set the smart contract up to understand where the bank contract is and how it works. And then so basically attack is this. It says bank contract deposit message value and then do the withdraw at the same time. Okay. And then when it receives the ether, it can call this withdraw function. Okay. So it's doing this on a loop because the receive function is the function that gets called whenever the smart contract receives ether. So like if I were to take out a MetaMask wallet and just send a transaction to the smart contract's address, it's going to call this logic. Okay. So basically it's calling deposit of 10 ether, withdrawal of 10 ether. And then whenever this smart contract sends the ether to the smart contract inside of this, all right, this line here on 22, payable message sender, which is a smart contract in this case, this function is going to get called. So what does this function do? It basically says if the account balance is greater than 0, then call the withdrawal function again. This is where it re-enters the withdrawal function before, it's doing it over and over again inside the same transaction. That's the key. Smart contracts let you do multiple steps inside the same transaction. And so if you keep calling this instruction over and over and over again, it's essentially creating a loop. Okay. And then when it's done, once it's drained, then it's going to send the owner the entire balance, and that's good. All the funds are going to get transferred to the attacker in this case. So we can see this play out in real time. Okay. There's a test inside of here. So this sample test, this is a hard hat test. So basically it shows how this works. So basically we have some basic tests inside of here that says, test deposits withdrawal of the bank account. So it's basic test to make sure that deposits work, that withdrawals work, and then it shows you how the attack works. So essentially we do some console logging. I'll close this down so you can see it. Turn it down a little bit. To see what the balance is of the bank, all right, and then the attacker's balance, and then we call the attack function, okay, and we do this with 10 ether, okay, and so we can watch the attack function get called in real time. Whenever the attack function's finished calling, you're going to see what the actual balance is. So you're going to see that it essentially drains the entire bank balance and it increases the attacker's balance. So let's just run that. You can see the instructions here inside the GitHub repository. Okay, npx hard hat test is what you do to run the tests. npx hard hat test. All right, pull this over a little bit. All right, there you go. So you can see the first test pass, accepts deposit, accepts withdrawals, the basic test. But then you can see what's happening inside the attack test. So the bank's balance before is 150, so it's a little bit higher than our initial example. This is the attacker's balance. That's just the standard balance that comes with hard hat accounts, okay? So the bank's balance after is 0. It's successfully drained all the bank's funds, all right? And then the attacker's balance is now this. All right, so that's an illustration of how the actual hack works. So if you're going to perform a reentrancy attack, which I'm not advocating that you go steal anybody's money, but that's basically how you would do it, okay? You would create a smart contract that calls the function that is vulnerable to reentrancy, and then you have some way to receive the funds and then keep calling that function while it's still inside the same transaction, okay? So now how can you protect your smart contracts against this reentrancy attack? Well, you can use a special library inside of OpenZeppelin called the Reentrancy Guard. Okay, so OpenZeppelin's a great, library set of tools for security purposes. You can get templates for certain, smart contracts that are community audited, like ERC20 tokens, NFTs, ERC721s, all that type of stuff. But they also have some great utilities that helps, safeguard any smart contract. So in particular, they have Reentrancy Guard, which you can see here. You import the OpenZeppelin Reentrancy Guard, And then you have these modifiers, which you can attach to your Solidity functions like this. So, non-reentrant. All right. You can just attach this, all right, to the actual smart contract. So step one, to fix this is you first need OpenZeppelin inside your project. You can see that inside the package.json file here. Okay. We've got OpenZeppelin saved here. So you make sure you want to install that. And then you can import the library inside your smart contract like this, OpenZeppelin contract security reentrancy guard. And then you want to inherit from the reentrancy guard. Okay, you can do that like this. You can say is, and then just copy this before the .sol. You can say is, this is reentrancy guard. Okay, that's the smart contract library from this file. So that's how you do inheritance inside Solidity. You say your contract bank, is reentrancy guard. And then you want to apply the modifier that comes with that smart contract. So you can see that's the documentation here. You can see the modifier is non-reentrant. All right, so you can just copy this. And then this is how you apply a modifier to your Solidity function. You say function withdraw, external is visibility. Then you can place your modifier here. You can say just non-reentrant. You just add that to your function name for the curly braces, and that will get all the behavior that's included inside this reentrancy guard. And if you're really curious, you can check out the source code to see what it does. You can see inside of here that it basically just keeps track of the function, whether it's been entered already. And if it has been entered already, then it just doesn't let you do it again. Okay. So it basically keeps track of the status. If the status is entered, then it won't let you enter it again. So you could code this out yourself if you really wanted to, but I would just, probably use a library in this case. So, let's see this in action. Let's go to our terminal and let's just do npx hardhat compile. Okay, to make sure our smart contracts still compile properly. I actually just did this off screen, so you'll see it compile properly. But now we can run the test. So we can say npx hardhat test. And what I expect to happen is that the first two tests that check for the initial deposit and withdrawal behavior should pass, but the second test where we try to actually do it an attack should fail. And if that happens, then we know that our solution here was successful. So let's run the test. All right. So boom, that's exactly what happened. So we can see the first test should pass. It accepts basic deposits and it accepts withdrawals. So the withdrawal functionality didn't change whenever we inherited this and applied the new safeguard, the reentrancy guard. However, you can see when it was trying to perform the attack that it failed. So error VM exception while processing transaction reverted with reason string, address unable to send value, recipient may have reverted. It worked. All right, so that's an overview of reentrancy attacks inside Solidity, how to perform one, if you can spot a reentrancy vulnerability. As always, I don't advocate for anybody stealing money on the blockchain. It's your responsibility to disclose a reentrancy vulnerability to a project. Hopefully you can get a bounty for doing that. Okay. And then that's how you also protect your own smart contracts against reentrancy attacks. So I hope you like this video. As always, smash that like button down below for the YouTube algorithm. Subscribe to this channel if you haven't already. If you like this video and you want to see more videos just like this on how to code blockchain applications, then definitely check out my YouTube homepage. You can find my free courses there. They're like Udemy courses, but they're totally free. And if you like those and you want to take the next step, or hey, maybe you want to take a master shortcut entirely, I actually become a blockchain master step-by-step from start to finish over at dappuniversity.com/bootcamp. You don't have to be an expert to get started today. I've helped people with zero coding experience become real-world blockchain developers in a matter of months. So that's all I've got. And until next time, thanks for watching Dapp University.